Me too. Like, me too. How are you like alive? Your brain.
Okay, everybody. So this is probably, ladies and gentlemen, this is probably a topic that you have not, guys.
I'm sorry.
I know, that's the point.
Sorry, I wasn't really there.
Okay, so linear programming. So let me just tell you a little bit about what it's. I kind of like it. I think it's sort of fun. You have some real world applications here. Can you imagine a scenario where, oh, I don't know, let's say you're a baker and you only have, you open your bakery for the day and you're like, oh, I only have so much flour left, or I only have so much sugar left. What should I make? Should I make more muffins or should I make more pies? What's going to make me the most money? I only have this much flour or sugar, whatever it is. Let me figure out what I should do in order to maximize the profit I'm going to make, right? So there are some real world applications of this. It's kind of fun. So we'll get there. But in order to be able to do these things, we sort of have to go back in our algebra brains and remember how to do a couple of things. So if you take a look at the first two, do you remember how to graph a system of linear inequalities? Well, good thing I'm here to help.
Thank you.
You're going to start by, let's all take a look at number one. You're going to start by graphing this like any other line. It's already kind of in y equals mx plus b. I know it's an equal sign, but otherwise everything else is in the right spot, right? So I can tell my slope, I can tell my y-intercept. So I'm going to start this line like I would any other line. I'm going to start at -3. And I'm going to follow the slope, which in this case is 2/3. So I would go up to the right 3. Okay, so I have at least 2 dots now. I would keep going if there was more space, but there's not, but no big deal. So normally we just come right in and we draw a line and we call it a day. But because these are inequalities, you kind of have to slow down for a minute because there's 2 different lines we could have. We could draw a solid line or we could draw a dashed line. Do you remember which one you do when? Go ahead, Angelina.
It's a solid if it's like equal to,
Yep.
and then it's a dash if it's only like.
Exactly. So if you, I don't know, I'll make myself a little key up at the top here. So if I am doing, if I have the or equal to bar, those are going to be solid lines. Right? Just like when we were graphing them on the number line, if I would put a solid dot there, I'm going to be using a solid line. If I don't have, I'm going to be doing a dashed line. Okay, so that's sort of my key. So with the equal bar, and again, I don't know why this sticks for me, so if it helps you, great. You have to use more ink to draw the bar, so I use more ink to fill in my line. Less ink because there's no bar underneath, so I do dashes. I don't know, that's how I always remembered it, and it worked, and it stuck, so there it is. So when I go back to number 1 here, I'm like, oh, okay, so this first one, it does have the bar underneath, so I do want to connect these with a solid line. There is another difference, though. When you are graphing an inequality, the line's not just your answer. By the way, that's the difference between them. If you have a solid line, you're saying points on this actual line are part of the solution. If it's dashed, you're saying not including the points on this line, but everything up to it. So the other part of this that you need to remember is that when it's an inequality, we're going to shade an entire region. And that region that we shade houses all of the answers that we want to talk about. So if I look at this, it says y is less than or equal to. That means I want to shade below the line because where are the y's less than this? Down below.
That makes sense. I remember this. Yeah.
Good. So if you're just graphing 1, I would just shade it in and I would be done. Right? So if I was just graphing the 1 inequality, there it is. You would just shade below the line in this case. You can test points. because sometimes our lines are not in slope intercept form, right? So if it's not in slope intercept form and you're not sure, you're like, oh, is y above or below? I'm not sure. You can always plug in a point. And if it works, it's part of the solution set. And you shade that side. If it doesn't work, it's not part of the solution set. So anywho, there's our first line. But now the second line, I have another one. So now I just graphed the second line on the same grid. I'm going to switch colors because I have that ability. You don't need to switch colors, but I might as well since I have it here, right? So if I'm going to graph my second line, again, it's already in the right form. So I know I'm going to start at a +3 and I'm going to go down 4/3. This time, however, notice how I do not have the or equal to bar underneath. So when I go to connect this line, I do not want to do a solid line. I am going to make it dashed. And now I need to ask myself, okay, well, where should I be shading in relation to this line? Can anybody tell me? Yeah, y is greater than, so where are the y's greater? Above the line. So I want to shade above this line. Now, since this is a system of inequalities, my final answer for the whole graph is going to be the one region that works for both of my lines. So what I need is I need to be below my penciled line, but above my red line. Do you see that the one region that works for both of those things is right here? So that whole region would be my solution to the entire system because that's the part that works for both. So usually when I'm doing these, I don't even shade until I only shade in the one section that works for both of them. So normally I wouldn't have even shaded this part in. I just did it so you could see where I was going. Does this make sense? Do you remember this? It's somewhere in there. Okay. So go ahead and try number 2. Same idea. We're going to graph each one. And then figure out the one region that's working for both of them. Me personally, you can see I sort of did it here. I draw myself little, when I draw the line, I just draw myself arrows. Do I need to be above this line or below? So then when I'm all done, I can kind of look back at it and be like, oh, okay, that's the one region that works for both. Thank you. We're just starting on linear programming. Okay, so let's take a look at the second one. Hopefully you got this one. We're lucky again. We're already in slope intercept form. Great. So I'm going to start at a -3 and I'm going to go up 4. 1, 2, 3, 4 over 1. When I am connecting the dots for this top line, should it be solid or dotted? Dotted, because I do not have the or equal to bar underneath it. So this should be a dotted line. Oops. Dotted, 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 dashed, whatever. And then I'm not going to go and shade. I mean, you can, but sometimes when you keep shading all these regions, it gets really confusing at the end. Especially what if you have 3 or 4 lines? Is that we're going to? So instead of shading a whole side right now, I just say to myself, oh, y is less than. Where are y's less than, above or below? Below, right? So I would put my pencil on the line and I will be shading below this line. So I just put myself little arrows to say, hey, when you're done, make sure that you're going to be below this line. You don't have to do that. It's not part of the graph. It's just helping me remember where to shade in the end. Okay, now I do the second one. Start at a +2, and we got a slope of -1. So I'm going down 1 over 1. Do I connect with a solid or a dotted line on this one? The second one is solid because it does have that bar. And then I ask myself, which way do I want to shade on this red line? It says y is less than or equal to. So I should be shading above or below the red line. Y is less than, I want to shade below, right? Because that's where the y's are less than, or down below. So I need to, now that I've graphed all of my lines, I just take a step back and I look, okay, well, where's the one region that works for everybody? And wouldn't you agree? I need to be below the red and below the pencil. So it's this one region right here. You can test this, by the way. So if you're not sure, right? If you're not good at the shading part, pick a point that you shaded over. Literally any point in here. Just pick a nice one. Pick, I don't know, 2, -2, whatever. You should be able to plug it into both your inequalities, and it should give you a true inequality each time. That's how you know you shaded in the correct region. All right, so everybody kind of remembers this little refresher. All right, so now we're going to get into the good stuff. It's going to seem real weird at first. Just stay with me, and then we'll get to the good stuff, okay? So before we get into a problem that actually models a real situation, let's just take a look at what in the world is going on. So if you look at the bottom half of the sheet here, let's see if I can get this up here. So when you have a linear programming problem like this, well, usually they come in the form of a word problem. And then we kind of create these equations. But since we're just starting, let me give you the equations, explain what they are, and talk about what we're doing. All right, so you're always going to have something called an objective function. So in this case, they've given it to us here. This is usually when you're trying to find a profit or a cost. So we'll talk more about that when we do a real problem. So that's our objective function. We actually kind of don't care about that until later on in the problem. That's like the second half. What we care about in the beginning are these constraints. The constraints are, what are you limited on? So for my example of the baker earlier today, the baker only had so much sugar. So I would write an inequality that says, hey, I only have so much sugar to use, so here's an equation that models how much sugar I can use. Or I only have so much flour, so I'll write another inequality that limits how much flour I can use. So anything that's holding me back, that's like, hey, you know, maybe you have, maybe you're sewing a product. Maybe you're sewing t-shirts and you're sewing pants, but it takes longer to sew pants than it takes to sew t-shirts. If you only have so much time in the day, which one's going to be more profitable? Should you be making more pants or should you be making more shirts? Where are you going to make your most money? Right? So those are the constraints. So you would set up an inequality for each constraint that you have, whether it's actual materials, it could be time, it could be whatever it is. All right. So once you have these things, here's what we're going to do. If you take a look at this box, I kind of give you the step-by-steps. We're going to start by graphing the constraints to find the feasible region. So the feasible region is just the one region that works for everybody. I have all these constraints. Okay, so what can I do? Where's my window of possibility? I only have so much sugar. I only have so much flour. I only have so much time. Well, what can I do? How many pies and muffins can I actually make? Like where are we? And then I'm going to take a look at that entire region and I want to find, all right, well, out of all the possibilities of what I can do, what's going to make me the most money? So that's sort of the gist. So let's go ahead and start by trying to graph the constraints to find the feasible region. So our first problem is that these are not in slope-intercept form, right? So I know you can graph them by leaving it in here, but with inequalities, it really is it's easier to have it in slope-intercept form. Because then I also know, oops, let me take that. I also know where I should be shading for each line. So I would say, especially with ones that are easy enough like this, let's just get them in slope-intercept form. So for the first one, all I'd have to do is add x to the other side. So I'd get y is less than or equal to a positive x plus 11. Right, you agree? It's the same thing. Don't forget, anytime you are multiplying or dividing by a negative, you're gonna have to flip that symbol over. But I didn't do that yet. On the second one, wouldn't I just minus x to the other side? So I get y is less than or equal to a negative x plus 27. And then the last one, I do have to do a little bit of work, but no big deal. So I'd have 5y less than or equal to a negative 2x plus 90. And then I do have to divide everybody by 5. But not that bad. There are my 3 constraints rewritten in slope-intercept form. Everybody with me so far? Yeah, okay, now we're gonna graph all 3 of these things. Let's see how we do. So I need to start for the first one. I'm gonna start at 11 and my slope is 1. Make sure you're always paying attention to the scale. So it looks like the scale is 1 and 1 on both sides, so that's good. All right, so we're gonna start at 11. On my y-axis, and I'm going up 1 over 1. You know what? I should give you straight edges. You're going to want nice lines. You'll see why. Two, three, four. Welcome. Welcome. Okay, these are all going to be solid lines. Now, for this one, where are you shading? Above or below this line? Below. Y is less than. Where are the y's less than? Below. So again, I'm just going to draw myself little reminder arrows that are not actually part of the graph. I just want to remember. Otherwise, you're going to have to go back and like redo each one and ask yourself again. It's so much easier if you just remind yourself. That was another tip from a student years ago. Also, they did reminder arrows, and I'm like, that's so smart. I'm going to do reminder arrows. And I've done it ever since. Okay, now I'll graph my middle one. Start at 27. And this one has a -1 slope. So here's what I like to do. I like to put the dots until they cross each other, because where they cross is actually kind of important. So now I'm like, yep, I know exactly where these two cross. So line that up. I'm also going to make sure that I draw my line all the way to the edge. So I never know where that feasible region is going to end up. So I draw my line all the way from one side of the graph to the other. Okay, so for this one, where do I want to shade? Above or below? Below again. So little reminder arrows. But now I have a third equation that I need to take into account. No problem. We're going to start at 18. And this one has a slope of -2/5. Oop, ding, ding, ding. I found where those two hit. I'm going to keep going to see where it hits the other line. Uh-huh. And this one's a solid line too, right? Yep. And where do I want to shade for this one? Down again. So I need to be beneath all three. A very common mistake is that when your three lines form a little shape in the middle, kids are always like, oh, let's just shade in the shape in the middle. Nope, not this time, because I want to be below all three lines. So that means the one region on this whole graph that works for everybody, isn't that going to be all this down here that's below everybody? So I'm going to take a minute here and just kind of really darken it so I can see it. Don't color it in so dark that you can't even see the points beneath it, but I need to make it dark so you can see it on the screen, especially. Okay, so this is what is referred to as the feasible region. So these, if we're, let's just pretend we're going with the example of, should I be making more muffins or pies? One axis is going to be number of muffins, one axis is going to be number of pies. So this tells me, hey, with the constraints that you have in place, these are all the combinations of things you could make. Does that make sense? Okay. Now, all right, great. That's well and good, but I want to make money. Or on the flip side, sometimes I either want to maximize my profit or I want to minimize my cost. Right? So I'm like, oh, which one costs me more to make? Does it cost me more to make pies or muffins? I might be looking at that aspect of things. But for now, let's assume that we are, I think this time we want to, what did I want to do with this one? Oh yeah, it says right here, find the maximum value of the objective function. So if you take a look at this particular one, you're either going to be doing one of the two things. You're either trying to maximize or minimize. So this one tells me maximize. This is where the objective function comes into play. Here's what we're going to do, which is so cool. I have this sort of two-dimensional shape that is my feasible region. I'm going to take the vertices where it's corners, right? The ordered pairs of those vertices, and I'm going to plug them into the objective function. And I'm going to see which one, in this case, I want to maximize my value. So I'm going to see what combination is going to give me the highest value. Does that make sense? You with me? Okay, so let's take a look at some of our vertices. So if I'm looking at the shape, it doesn't matter what order you start in. So if I just, I'll circle them. So there's one right there. There's one. There's one. And now we do sort of bound off the negatives. So I don't have, sometimes in the constraints, it'll literally be X can't be less than 0, Y can't be less than 0. I actually don't have that here. So, and it doesn't matter since I'm trying to maximize my cost. Obviously making nothing wouldn't maximize anything for me. So I can, because I don't actually have a, right, this region actually does keep going into the negatives because this one didn't stop us. So the only vertices I really have, oh, so I guess that one's not even really one either, is it? Because I'm not bounded this way. It's really only these two. I didn't even think about that. Sorry. It's not going to hurt to have that one in there, but it's not actually one of my vertices because this just keeps going. So I've got these two. So what am I gonna do? I'm gonna figure out what their ordered pairs are. So this one is at 5,16. So this vertex is at 5,16. And then this one is at 15, what's that? 11. Is it 1512? Yeah. So once I have my vertices, however many there are, in this case, there's really only two that I'm looking at. I'm going to take that objective function, which was z equals 4x plus 6y. I summed this up in the box too, so if you're looking back on this later. So all I have to do is take both of these coordinates, plug them in for x and y, and see which one's going to give me a greater value. Isn't that neat? So in this one, 4 times x, 4x is 5, 6 times y is 16. So this one gives me a value of 20 plus, what's 6 times 16? 96. So I get a total value of 116 from that one. Now I do the same thing. I'm using the same z equals 4x plus 6y. But now I should write this down here. Now I'm going to do my second vertex and see if this one gives me more. So 4 times 15 plus 6 times 12. Let's see what we get. 60. 6 times 12 is what, 72? $132. So if I want to maximize, let's assume that this is profit, I would want to do 15 of x and 12 of y. Does that make sense? It's kind of neat, isn't it? The hurdles that we have are coming up with the constraints. Those can be tough if you're just given words. But I'm going to guide you through it. So, shall we give it a shot? Is everybody okay so far? Have I lost any of you? Do you understand what we're doing here? All right, cool. So let's see. Let me see which I might not want to do. Oh, I give you another. Yeah, let's do that. All right. So before we do a word problem one, flip to the second one. This one. Yeah, let's do this one real quick. And this one, you'll notice that we do sort of section off the negatives. Okay, so the objective function, remember, I don't actually really care about that until later. That's like the second half of the problem. So first, you're going to graph all of your constraints. So let's all take a moment, graph your constraints. So if x, everybody's a solid line here. Wait, by the way, just if you're confused about this, if x has to be greater than or equal to 0, that's this line, right? Here's the line x equals 0. If x has to be greater than that, which way am I shading? To the left or to the right? To the right. Right? Because I don't have an up or down if it's a vertical line. Everybody else, I can do that up or down trick, but the x ones I can't. I just have to ask, well, where the x is greater than? Oh, it's this way. All right, y's are just going to be here, right? So I've got to be above this. Now, the last two are not in slope intercept form, so I might take a moment and just get them there. Oh, I remember why I didn't like this one, because it's super hard to graph that last line, but whatever. We'll make it happen. Okay, everybody has theirs rewritten into slope intercept form. Okay, so I have the first two graphed already. It's just the x and the y axis. Now I'm going to graph this one. Y is less than or equal to negative 1/3 x plus 5. Okay, start at 5. Check my scale. Oh, be careful. What? What's the matter? What's the matter?
That's -5.
Oh, it's not. These are just, it's just the other side of the graph.
Oh, okay.
Sorry. Yeah, I noticed that after I printed them. It's just the grid continuing. You get what I'm saying?
Yeah.
Yeah. So that's still your origin. The negatives are still down here. Sorry. All right. So there's, but you got to be careful though. You're not going to go, oh, I guess you could on this. Because you got to look at your scale, right? One whole unit is down here, over 3 would be over here. Since they're both like that though, if you did just do one box, it would actually line up. So you get into, oh, that was something on the test that people were using, like the if you look at your, I know you don't have it in front of you, but on the test, the scale was different right here. Just to show you real quick, because I know you probably don't have it. But this one goes by 10s and this one went by 5s. So some of you were just counting the boxes and saying like, oh, up 1 over 1. Because this isn't 1 and that's not 1. You get what I'm saying? Scale matters. And if the scales match on both sides, then it's fine, like they do here. Both of them, each line is what, 1/4 on both sides. So then it doesn't really matter if you go up 1 over 1. But if the scales are not the same, it matters a lot. Any hoosers. All right, so we went down 1 over 3. We're going to have a solid line. And we're going to shade below, right? Because we have y is less than. And now this next one is tricky given the scale that we have. I know normally we'd start at 16, right? And then go down 4 over 1. I don't have a 16 on my graph. So I can't get there. I could graph by intercepts. Yeah, so x has to be 4, doesn't it? Mm-hmm. So I'm going to be there. And then I can figure out I know the slope is a -4, right? So I can't go down 4 over 1, but I can go up 4, back 1, and ding, ding, ding. Look, they hit right there. So this is what this line looks like. And then I ask myself, where do I want to shade for that one? Y is less than, so I want to be below that line. So do you see the feasible region? It's going to be basically this quadrilateral right here. I'm going to take a moment to kind of shade it. And this one does have these, we had x has to be greater than 0 and so does y. So I do have 4 distinct corners here. If on your homework, you enjoy coloring and you want to color, maybe you got some nice colored pencils at home, or markers might bleed through, but I mean, you do what you want. I encourage you to add some color if you want. All right, so everybody has their feasible region. So far, so good. All right, so all I need to do now is pull out my vertices, my corners, right? So I'm going to list just all my ordered pairs. And where will I stick them? I'll put them right here, whatever. So I have this one here that's at 0, 5. I have 0, 0 is 1. I have 4, 0. And I also have 3, 4. Okay, does everybody agree? There's my 4, and I want to maximize the objective function. So I already know one of these is not going to be the answer, right? Who's already out? 0, 0. There's no way. If I don't make any, that's not going to make me any money. So I don't even have to bother with that one. The answer is just 0. But now take that objective function, remember, which is just this z equals 3x plus 2y. So for each one, I'm going to do 3x plus 2y and see which one gives me the highest value. So this one would be 0 plus 10, right? Which is, I get 10 from that one. This one would be 12 plus 0. So I get 12 from that one. This one is 9 plus 8. So I get a 17 there. So looks like I have my winner. Thoughts? We feel all right? Okay, I'm going to take that as a yes. Now, since we don't have a ton of time left, I don't think we're going to get to word problems today. So why don't I stop it here, have you do the second one down here for tonight's homework. May I just caution you on one thing? When you are rewriting these into slope intercept form, right here, aren't you going to minus the 3x and divide by a -2? And what happens when you divide by that -2? You flip the sign. So in fact, why don't we do this one? Because if you shade the wrong way on one of them, your entire feasible region changes, right? So it's really important to make sure that you've got these right. So I'll just do this one with you to make sure, because the other ones are all going to be fine, I think, yeah. So this would be a -2y that are equal to, oh, okay. So we're gonna minus 3x to the other side. Now you gotta divide everybody by a -2. So that's gonna flip that symbol right on over. So that should be the equation that you do for the second to last one, or the inequality. I keep saying equation, they're not, they're inequalities, sorry. Oh, and this time, look at your directions here. You want to minimize the objective function this time. So now you're trying to get who's going to give you the smallest value. Does that make sense? So you're still going to get your vertices, whatever they are. And I know what you're thinking. Well, wouldn't it just automatically be 0, 0? You don't know that 0, 0 is part of your feasible region. I'll give you a hint. It's not. So yeah, we don't know what it is yet. All right, so give these a shot. Tomorrow we will work on the word problem aspect of these, which is super fun. Hopefully you like it. All right, so all this stuff, I will open it up on Jupyter in just 1 second. I'm gonna do it in here.
No.
Does everybody have what they need from what I have on the screen? Or can I take that away now? Yep. Sure. Give me 1 second. How do I lose things so quickly? There was a Slippy. And it's already, it's literally just as weird. Whatever. Make do without it. Oh. That's this shaded area.
Inside this.
So everything in there would be possibilities. So you're just looking at the corners to plug into this. And see which gives you the highest rolls. Is in or is not?
It's not.
Oh, so like if you,
Because I can't use it.
exactly.
Oh, I see.
Yeah. So don't do it that way. You could do, well, you have the slope, right? 3 halves, and then go back to this. Wouldn't X have to be 3, right? Pull that up. So start at 3 and then just follow the slope. Okay.